Everyone, my name is Felipe Alarcon. I'm a PhD student at the University of Michigan. The talk that I'm going to give you today is about the chemical gap theory applied to AS09, revealing the chemistry of planet formation. So the outline of my presentation, I'm going to give you the introduction and motivation of my work, then the methodology, after that the results, and finally the conclusions of my work. So to introduce the topic, basically we know that protoplanetary disks are circumstellar disks that are the birthplaces of planets. So usually during these 5 to 10 mega years that a protoplanetary disk live, all the physical and the chemical processes that take place there will shape the initial and reservoir of protoplanets and the final architecture of the systems. So in order to fully understand the planet formation process, we also need to understand how the disk evolves and also how the chemical conditions will be shifting during this 5 to 10 mega year process. So from the D-Chart survey, which is the image that I'm showing you here, we know that particularly in a subsample of 20 disks, most of them show, or all of them show, dust substructures in the dust emission images. So among those substructures, we can observe gaps, rings, and spirals. So we can link all these substructures to be induced by planets or some other mechanisms that we're not completely sure, but we know that if a planet is forming, it will be linked to a substructure. So our talk is basically about chemistry. So chemistry will be important because that it will be end up forming the atmosphere of a planet, the rocky core, and also that will end up forming life too. And that will be linked to the gas, not to the dust substructure. So we wonder whether or not we can link these dust substructures to actually gas, to be gas substructures, and what type of chemical effects we can expect out of them. So in our work, we focus on AS209, which is one of the 5 sources observed in the ALMA-LARGE program of chemistry in planet formation, or MAPS. I'm only showing you the figure, the emission profiles for CH2O, C2H, and in the green line is the dust continuum profile. So we can observe that CH2O, which is usually used as a gas column density tracer, has a very wide web in emission that doesn't correspond to any substructure in the dust. And also C2H, which is a photochemical tracer, has a peak in the wide gap in CH2O. So this presents a degeneracy problem where we ask ourselves, is the CH2O feature a gas feature, meaning a depletion of gas in the disk, or is that some type of CO chemical processing taking place? And how that solves this correspondence between gas and dust in the disk. How we actually model and solve this? So we ran 2D thermochemical models with the code RAG2D, and we model all the chemical evolution of AS09 with a static structure. So we have 2 sets of models. In model A, we say that all the CO structure is produced by a CO depletion in the disk, meaning that the disk has a smooth gas surface density profile. And we also try different small grains content or depletion in the disk. And I will explain that later, and that's because we also use C2H, which is very sensitive to the small grains content. In the model B, we use the infer CO column densities derived in Shank et al., which is part of the collaboration as well. And in this case, the CO depletion will be a tracer of gas depletion in the disk, meaning H2 surface density depletion in the disk. So this is basically the depletion profile that we use, and it's the one used by Shang et al. In the collaboration. And on the right, we also use a variable C2O ratio in the disk, where we increase the C2O ratio by adding extra carbon in a particular range that it's necessary to explain the C2H column density that we observe in the disk. And this is mostly linked to the C2H rather than CO, but that's necessary as well. So the results, first we look at the CO column densities and compare them with the ones inferred from the data. by Coco Chang. So basically, in both sets of models, we see that changing the small grains content or adding a gas cap or a CO depletion, in both cases we can solve and we get results that are similar to the condensation frame from the data. So this didn't solve the degeneracy. So we have to go to other mechanisms to try to solve this. However, we can see that the vertical distribution of CO in the disk is different within the two models. So basically, when we deplete the CO, we deplete the CO all across the disk, and we'll see more vertical structure. This could be important if we are able to have a set of CO lines that will be tracing different layers of the disk, so we can expect that those different lines of CO will have a different behavior in each one of the models that could potentially solve the degeneracy. But we will actually need those lines to do that. So we also try comparing the emission heights. So in our models, we use the regions or the layers where the optical depth range between 0.67 and 2 in the disk, and compare that to the emission heights from the data inferred by Charles Law and collaborators. So we can see that basically in both models, our emission heights from the models match pretty well with data. They have a small shift for both CO in the upper panel and 13 CO in the lower panel, but nevertheless they are within the uncertainties of the data, so we can't really discriminate between the two of them yet. So then we use C2H, which is usually for the chemical tracer, but it's very, very bright in protoplanetary disks. So in this case, we observed that in both models, it didn't really change the column density due to a gas cap, meaning that C2H is insensitive to gas depletion in the disk. However, it will be very sensitive to the C2O ratio. So Bosman and collaborators in the MAPS group show that basically to explain the high column densities of C2H, we need a very high C2O ratio. And when we use the gas cap, we can observe the same. So it's not because we have a gas depletion in the disk. Also, we see that it will be sensitive to the small grains content within a factor of 1 order of magnitude, but that's still significant. So even though we cannot explain or solve this linearity between a CO processing or a gas cap, we can see that C2H will give us constraints about the C2O ratio in the disk and the amount of small grains. So after that, we have to use the pressure fields. So Tick and collaborators a couple of years ago, they inferred the pressure profiles using the disk kinematics in AS309. So in our models, we have a hydrodynamic structure, so it's just a proxy of the pressure profiles. So in the images, in the black lines are the emission heights. The dashed line is the cut made by Tick and collaborators, and the dotted line is the cut that we also use the dotted line as a lower bound for the CO emitting height in the disk. So we compare our pressure profiles from the models with the one from Tick and collaborators, and basically we can observe that when we have a gas cap, we also see a big dip, which is roughly an order of magnitude in the pressure profile. So even though our models are static, if we add the dynamics of the disk, the meridional flows would make this dip even deeper in the pressure profile, not shallower. So we see that the fluctuations in the pressure profile of the disk are very small, within a factor of 2 or less, and they seem to be consistent with a with the model without a gas cap and just CO depletion. We cannot discard any gas surface density fluctuation in the disk, but if there is a gas surface density fluctuation in the disk, it should be rather small to be consistent with the inferred pressure profiles from the observations. So the pressure profiles solve the degeneracy, and we can tell that the main cause of the CO emission in the disk is because of CO processing and not because of a gas cap. So the conclusion of our work basically, CM emission presents a degeneracy between either features in the H2 surface density or some chemical processing in the disk. Condensity calculations of both scenarios did not solve the degeneracy, neither the emission heights. But when we go to the pressure profiles, we were able to solve this problem, and we can say that basically CR processing is more important than a gas depletion in the disk. And also because we know that we have a gas depletion disk, it will cause a dip in the pressure profile. We can put an upper limit on the presence of any planet in the disk, if we can model and know well enough the dynamics that is happening in -09. Also, we know that C2H, which is another chemical tracer, doesn't really respond to gas surface density, but it rather does to the UV field, which will be sensitive to the UV luminosity from the star and the dust grains present in the disk. And also, it's important the C2O ratio. Even though this doesn't solve the generality problem, it can tell us about the chemical evolution of the disk, which is very important to understand how the chemistry evolves around planet forming regions. So with that, I will finish my talk, and thank you for your attention.